Okay, it looks like it's recording. All right, so we have, in this class, we have an exam coming up next week. Okay, so that would be on Tuesday at 11 a.m. And my idea here is I want, hopefully, Brandon and Irvin, you can have your cameras on. If you don't have a camera, you'll have to hopefully borrow one for Tuesday. All right, and you'll have an hour and 15 minutes to work through this part one of the first exam. And then the second part is going to be more of a take home kind of thing where the problems will be a little more complex, although not a lot more complex. And you'll have time to think through those, and you can ask me questions if you get stuck on things. I prefer you not work together on that part though. Okay, so what I wanted to do today was go through and show you a few problem types like might be on the online portion that shows up next Tuesday. Did you see that review video that I already put up about that? Okay, so hopefully that makes sense to you, but if you have questions about that, certainly you can ask questions about it. So let's get started with this. The first thing that I wanted to do is tell you there'd be some multiple choice type questions, and I worked out one as an example. Just a second. Okay. Okay, so hopefully you see the screen share. In this example, I have a multiple choice question where I'm asking, you have an input signal and it's an impulse function. All right, choose the best description of the output response, and we have different names of responses. And so it turns out, anybody want to take a stab? What do you think is the best answer? You put in an impulse.
Is it the step response?
Well, that's a good guess, but if you put in an impulse, you get an impulse response. So if you put in a step, what do you get, Jared?
A step response?
Step response, yeah. So sometimes a problem is so easy that it makes it hard. All right, so this one's so easy that you can make it harder where you get tripped up on it. So if you put in an impulse, you get an impulse response. Okay, so that's one of the points that I'm trying to drive home with this, the difference between different responses. If I wanted the ramp response, I would put, R of t is equal to t, u of t, and that would give me the ramp response of the output. Okay, so you put a signal in, you get something out, and typically you can name those. Okay, next, an example problem like I would have on the exam would be, take the inverse Laplace transform of this, okay? And given that I'm going to allow MATLAB, that becomes a pretty easy problem because you can literally just type that into MATLAB and get that response. But that's okay. I feel like you could also do it by hand. And so what we're trying to do here is get where we can use the tools and apply those to control theory. And I think if you show me you can use the tools in MATLAB to find inverse responses, that'd be good. And, I might have something like f of t is equal to t e to the minus 6t cosine 3t. Find the Laplace transform. Again, you could use MATLAB for that, and you just type that in and find the Laplace transform. Okay, but what we're seeing here is this idea of going between, the time domain and the S domain, and this type of question is supposed to illustrate that. Okay. This next one, I took examples from old tests, and here's an old test example where I probably would not do this on this take-home portion, because what's tricky is this e to the minus s. Now, if you type this into MATLAB, MATLAB would get the right answer. But e to the minus s, when you see an e to the minus something, like e to the minus 3s or e to the minus 2s, all those indicate a time shift. It's the time shift property of Laplace transforms. You may not remember that from ODE. We haven't really dwelled on it too much because we don't typically do a lot of shifting of signals, but I did want you to know that that's there. And the MATLAB can figure that out. So it would show you a time shifted answer. Okay. All right. Next, here's one I really wanted to spend some time with, because this one you can't use MATLAB for. A problem like this you can't use MATLAB for, and it helps me determine whether you're getting the idea of what the response is going to be based on a pole pattern. Okay, so what I have here is 9 different pole patterns, and you're supposed to match those to the signals. Okay, so let's take some time and work through that. All right, so just to help you get oriented here, if I zoom in here, signal label or pole pattern labeled A is just a single pole at -1. It's kind of hard to read that, but -1. Okay, and B is a single pole at -2. All right, and then C, you can tell the difference here. C, this is the 0 point. So Z is this pole is actually positive. Okay, so let's think about those two. So in my mind, I picture something when I see a single real pole. How about you? What would you think of as the time response? Let me give you a hint. If it was a single real pole, like at s equal -1, this would be something like 1 over s plus 1. Okay, and so I think of the inverse Laplace transform, it would be e to the minus t. I have that one memorized. You may not have these memorized, but okay. And so if I compared that to part B, what would you get for part B? What do you think the response is?
E to the -2.
Yeah, it's proportional to e to the -2. Okay, and then how about part C? If that's a 1, I'm not, it may be more like yeah, it's a 1. This is a 1 right here. What would that be?
E to the t.
E to the t. Okay, so I look down at my choices here, and I'm trying to match those up, and I have an idea of what an exponential looks like. Okay, so I see 2 decaying exponentials, and then one that's zooming up to infinity. Okay, so this one matches the e to the t. All right, so that matches the, that would have a 2 here, because this is signal 2. Okay, and then how about the difference between A and B? A is e to the minus t, which doesn't decay as fast as e to the minus 2t. Okay, so 5 looks to me like it's decaying slower than 7. All right, so this would be 5. Whoops. And this would be 7. You get the idea? So I'm trying to get the association in your brain about pole patterns and what the corresponding time function looks like. All right, so we move to the next row. Here's a pole pattern, and this is at 0. There's a pole at the origin. Okay, so in my mind, I think of the unit step function. Okay, so I look through here and, you know, signal 3 is just, I keep hitting the figure button. Signal 3, I'm trying to get that where I won't do that. That's a 1, and so it's just a constant. So that would correspond to D. Okay. Now, when I start looking at E and F, okay, E and F have complex poles. Okay, and if I zoom in here, they're both at -1 for the real part. And so I'm looking at, well, what is the difference? Well, the difference is part F, the complex of the imaginary part, is larger, more spread apart than for signal E. Okay, so what I'm expecting here, whenever I see complex conjugate pairs, remember I had a video on that, I'm expecting a sinusoid that decays in time according to e to the minus t in this case. All right, so I go and look and I see I have a couple of cases of that. Here's one, here's the other. Okay, so I also look at this and I say, well, what's the difference between 8 and 9? And I see that 8 oscillates faster than 9. Okay, so 8 oscillates faster than 9. All right, so which should go here? Is it 8 or 9? And which should go here? Is it 8 or 9?
Should 8 be with E?
Well, 8, which does 8, unfortunately, I can't have both on the same page. 8 oscillates faster.
No.
Okay, so the imaginary part gives you the omega naught. All right, so I think it's going to actually be 9 for this one because this omega naught is smaller than this omega naught. So if you have a larger omega naught, it's going to oscillate faster. Okay. All right, so you get the idea of what we're trying to do here. We're trying to just get to where we can visualize what signals look like and get an idea of the speed of the signal. Does it decay fast? Does it oscillate fast? And look at pole patterns, you can make that association. Okay, how about G? What are we thinking here? Again, this is 0. So this is 1. So our real part for these two poles is positive. Okay, so this thing is going to grow up as e to the t. It also has an imaginary component, so it's going to grow up, but it's going to oscillate at the same time. All right, so if you look at 6 is shooting up and also oscillating. Okay, so 6 would match here. All right, and then the last two. Okay, on the last two, the real part of the pole is 0. Okay, so e to the 0 is just a constant. So I'm expecting a term that oscillates, but it doesn't decay. So we're just going to get a sinusoid back. All right. So how do you tell the difference between H and I? I look at that and I see 1 and 4. Those are two signals that oscillate and don't decay. All right. 1 oscillates slower than 4. Okay. So which one should H be? Is it 1 or 4?
Is it 1?
It's 1 because this omega naught is smaller than this omega naught. And so then this would be 4. Okay. So, you know, it's not something you should memorize. It's I mean, you memorize certain shapes, like, you know what e to the minus t looks like, you know what e to the minus 2t looks like. You know that e to the minus 2t decays faster than e to the minus t, all right? And then, you know, if you have a bigger omega naught, you oscillate faster, all right? And then you also know if you have a pole that's on, we call that on the right half plane. If you have any poles on the right half plane, the signal is going to grow unbounded, okay? All right, so there'll be a problem like that on the online test that you'll take on Tuesday, okay? Where you have to understand the relationship between the pole pattern and the time domain signal. Okay. Let's move on. All right, here's another example I wanted to cover with you real quickly. This is the last one, I think. Yeah. Okay, this is the last one. You know, the exam would be longer than this, but I wanted to get you started on studying. I'll post some more review things up on Canvas as I come up with them. Okay, so here's a system that's described by a differential equation. So I think you can see where we're going in the course. We're now concentrating in Module 5 on writing differential equations for circuits and also for mechanical systems. And so we're trying to control these things. And so if you can write the differential equations, you can come up with a math model for the system that we're trying to control. Okay, so one of the things we've talked about several times is if you had an ODE, can you write down the transfer function? Okay, and so I can do that by inspection. The transfer function h of s, which is y of s over x of s, is equal to, and then on the bottom, what I do is I look at this y double dot, and everywhere I see a double dot, I put an s squared, and the coefficient in front of that is 1. Okay. Then I look at 8y dot. Okay, so if I see a dot, I put an s. And I have the coefficient 8, I forgot to put down. Okay, and then finally 15. All right, and then on the top, I have x, so that would just be a 1, and then x dot, which would be s. Okay, so you know what we did in the past is we took the Laplace transform of both sides of the equation, did the algebra, and but it always turns out to be the ratio of the x coefficients divided by the y coefficients, where you use the powers of s to represent the derivatives. Okay, so there you are. There's the transfer function of the system. Okay, so if I wanted to find the impulse response, what would I do?
Don't you multiply by 1 over s?
Okay, it's the impulse response. Okay,
Oh.
so when I have the impulse response, y of s, you're right though. Y of s is h of s times x of s. For the impulse response, x of s is equal to 1. So a lot of the difficulty in the class is really understanding the terminology. Okay, so impulse response means the input is an impulse. Okay, so x of s is equal to 1, and so what I'm expecting is y of s is the inverse Laplace transform. Okay, I guess if you're going to use MATLAB, you have to spell it right, but inverse Laplace of y would be the impulse response. So hopefully everybody's had good luck with using MATLAB to do the calculations. So this problem is actually really easy if you let MATLAB do the work for you. So the inverse Laplace transform there would be the impulse response. Okay. All right, so now in part C, we're asking for the unit step. Okay, and so now what would we do for y of s? What is x of s for a unit step?
1 over S.
1 over s, right? So now we just add in the extra term and use MATLAB to do the inverse. Okay. And what you'll see is you'll get a certain type of response. Let me do the pole zero pattern first before we do that. Okay, so if I look at the pole zero pattern, okay, here's the pole zero diagram. How do I get the poles? If this is h of s, what are the poles? Well, to get the poles, you need the roots of the denominator. So I can try to factor this. And 15 is 3 times 5, and 3 plus 5 is 8. Okay, so I know this factors into 3 and 5. Okay, so if I did the pole zero diagram, I would go over here 1, 2, 3, 4, 5. And I would put a pole at -5 and a pole at -3. And then I have a 0. Remember, make a 0 for a 0. A 0 is at -1 because you set the numerator equal to 0. So there's the pole zero pattern for this system. Okay. So once I have the pole locations, I can come up with the form of the solution. Okay, so if I was looking at the impulse response, the form of that solution would be A over, let me do it like this. I envision the partial fraction expansion like I learned from ODE. The form would be A over S plus 3 plus B over S plus 5. You do that partial fraction expansion to get the form of the solution. And so H of t would be A e to the minus 3t plus B e to the minus 5t. Good, that's the form of the solution. We could get the exact solution if we calculate A and B, which we can let MATLAB do. All right, so I let you use MATLAB to do these inverses, but once I have a pole zero diagram, I don't need to have MATLAB to tell me the form of the solution. Okay, I'll know roughly what it looks like in terms of the components, the e to the minus 5t component and the e to the minus 3t component. All right, so that's what I'd like you to be able to do so that as you work through examples and projects that we do in here, you get a feel for what's going on. Okay. All right, so the other two questions I pasted in were from a previous exam. We haven't covered these two items yet, so this is a good representative example of some things I'd like you to do for the exam. So, okay, so that's all I wanted to cover today in the check-in session. You saw the video about the exam review, so hopefully, if I were you, I would pay attention to that. I'm not going to have any homework that you turn in on Sunday since you're studying for the exam. Okay, and then what we're going to do is we're going to transition into the take-home part, is where you do some of the modeling. So you should this week, so you don't get too far behind, try to watch all the stuff from Module 5 about how do you model circuits, okay? Because the way that Professor Miller did it, I think is a little confusing, especially for mechanical engineers. All right, so I have a new approach that I'm doing on that. You can see what Professor Miller did under the optional section, but you would be able to use just the Laplace transform method that I talk about in Module 5. So be doing that so you'll be ready for the take-home part that I'm also going to give you next week. So, all right, any other questions about,
I have a question.
yes,
So the take home part is mostly going to be like module 5 stuff.
it'll be module 4 and 5
Okay.
and actually kind of pulling it all together. So maybe
Okay.
I would have you, here's this system, write the differential equation, here's some, convert that to a transfer function. If I gave you some numerical values, you'd be able to do plots of the impulse response and the step response and things like that. So,